So first up, we're going to have Koji Takahashi, who's a senior economist at the Bank of Japan. And I'll hand over to Koji now. Thank you.
Okay, thank you for having me in this session. So let me share my slide. Okay. Can you see my slide?
Yep, that's good.
Okay, let's get started. Oh, sorry. Okay. Okay. Hi, I'm Koji Takahashi from Bank of Japan. I want to thank organizers for having me on this session today. And I'm very excited to share our research with you. And our paper is about the application of mobility data for macroeconomic nowcasting. And this paper is joint work with Kohei Matsumura, Yusuke Ao, and Tomohiro Sugo. And all of us are from Bank of Japan, so the usual disclaimer is applied. Okay, let's get started with motivation. Our study is, of course, motivated by the pandemic of the COVID-19. Obviously, the importance of evaluating economic conditions in a timely manner has become extremely important. However, the official statistics won't tell you much about the situation of the current economy. So it is natural to try to find non-traditional and high frequency data to address this issue. And we focus on the mobility data because they become available with just a few days lags. Okay. And what we do in this paper is that we focus on GPS data and construct indexes to nowcast traditional statistics. And to do so, we combine GPS data with other data that tell us what the type of facilities are located at each place. Then we examine in which industry and in which sector the GPS data are useful for nowcasting economic activities. And it turns out for some sectors, GPS data are quite useful for nowcasting activity. And the contribution of our paper is very simple. We show the usefulness of mobility data as a tool for macroeconomic nowcasting. So the outline of my talk is follows. We first explain the data we use and show the application to service industries. Then we also use the data for manufacturing industries. Okay. So what the data is? Our main data include estimate of hourly number of people at each mesh, which is called each place, which is called a mesh. A mesh is defined as 100 meter by 100 meter square, characterized by pair of longitude and latitude of the center of the mesh. And in our data, there are 20 million meshes covering all over Japan. So data are essentially a huge panel of data. The cross-sectional unit is mesh ID, as shown in this table as an example. And it has 34 billion records in total. But it is easy to imagine that even though we know the number of people sitting in a certain place or mesh, we never know what they are doing without additional information telling us what the place is for. So what additional information should we use? Of course, it depends on your goal, right? When we try to nowcast production, we use economic census microdata. And for food industries, we use the API of restaurant guide service. On top of that, we can infer from the GPS data itself. Suppose, for example, the population in a mesh increases during daytime and decreases in nighttime. Then we can be sure that it is unlikely to be a residential area. Also, we can use machine learning technique, but we didn't investigate the potential of this approach in this paper. Our first target are service industries. We thought it is a good starting point since in many service industries, the sales is directly driven by people who stay in the shop. We focus on 3 sectors specifically: so amusement park, shopping centers, and restaurants. And to pin down relevant meshes and exclude noise, for each sector, we use a different mixed strategies. So sometimes prior knowledge is quite useful in removing noise, as in the case of amusement park. In the case of shopping mall, I use also other dataset. Finally, for food service, we also use some statistical method to disentangle useful meshes from noisy meshes. Okay. Now I show you the result. Amusement parks are quite large in general, so we can identify by hand all meshes covering each park by checking the park on the map. Also, the number of parks is very limited, so it's feasible to do this for all major parks. The left here shows a pattern of hourly population for the selected meshes. The density is relatively high in the daytime or weekends, as well as on Mondays and Fridays. Oh, sorry. Which is very reasonable if we think about the amusement parks. The right figure shows the year-over-year change of population index aggregated at the monthly frequency on selected meshes. And gray line is official statistics. Their positive movement illustrates the usefulness of GPS data. Okay. Our next example is shopping centers. This time, manual checking every shopping center on the map is infeasible because the number of facilities is large, about 3,000. But fortunately, addresses of major shopping centers are collected by the Japan Council of Shopping Centers, so we use that. However, even though they are on the shopping center list, the population fluctuation can be affected by irrelevant type of activities, such as commuting by trains. Because in Japan, usually the shopping center is located close to the stations. So we exclude such meshes using data for addresses of stations. Also, we believe that population in weekends should be larger than that of weekdays. So meshes whose distribution doesn't satisfy this property are also removed. The resulting population index shown on the right-hand side, again, tracks the sales index very well. Okay, in the food service sector, the size of restaurant is much smaller than 10,000 square meters in general. So I said the minimum unit of the mesh is just 10,000 square meters. So even though we can pin down the address of every restaurant, further techniques should be adapted to remove unrelated population fluctuations. So we use a well-known clustering method called K-method to disentangle activities taking place on selected meshes based on restaurant guide service API. We set the number of clusters equal to 5 and examine the population fluctuation in each cluster. One cluster, which we refer to as cluster 1, exhibits reasonable pattern of hourly population. Its peaks at noon and 7 p.m. weekdays, implying this cluster successfully captured visitors to restaurants. The population index for cluster 1 shows similar fluctuation to our target indicator called JCB consumption, which is a consumption index developed by a private company based on credit card data. So next target is production. Basically, what we want to do is to approximate the production function using only proxy for labor input. So it is natural to expect that nowcasting performance depends on the shape of true production function. Let's take a look at to what extent the production function can be approximated by ideal labor input. This table shows the correlation between industrial production and labor input obtained from official statistics. So it is clear that even we obtained an ideal proxy for labor input, we maybe cannot nowcast well the production in sectors like food, beverage, and tobacco industries is shown on the bottom of this table because the correlation between labor input and production is very low, almost zero. So we focus on sectors how the correlation is high, such as production machinery and transportation equipment. To identify the meshes related to the production of each industry, first we choose representative factories. Among factories listed in economic census microdata, we choose factories whose area about 10,000 square meters, and those are ranked in top 10,000 factories in terms of production value added. The selection meshes are a little bit complicated compared to service industries, even though we know the site area of each factory from census. This is because we know only the area of factories and we don't know the shape of them. So we don't have prior knowledge about how to choose meshes surrounding one containing the exact address. So one heuristic approach we adopted is first, we collect the meshes so that the sum of the area of the collected meshes exceeds the area of the factory. Second, we remove unrelated meshes in this set based on the distributional features. So what is the distributional feature of factories? This figure shows population pattern on typical factory area on the top and residential area on the bottom. Over day, or week, and over 24 hours. And you can easily find the difference between them. In the factory area, the density is near zero on Sundays, since no workers work on Sundays. And within a day, it has an inverted U shape. The residential area has the opposite pattern. This implies that we can distinguish true factory meshes from less related ones by checking their distribution. And one straightforward way to implement the idea is to set thresholds for Sunday ratio and daytime ratio so that population are aggregated on filtered meshes show a highest correlation with official statistics of labor input. We also add a third measure, lower threshold for the average population. So we choose each threshold based on the correlation. And this table shows the thresholds for each sectors. So the aggregated factor-related population and labor input displays strong positive co-movement, so implying our strategy is working. Then, next, we want to use factor-related meshes to nowcast the industrial production. Another complication is that the core working hour is likely to differ across sectors. Again, we conducted a grid search for 3 parameters, determining the time window, such that population aggregated on window has the highest correlation with official statistics. For example, in transportation equipment sector, if we compute the sector population index by aggregating population from 5 p.m. to 6 p.m., including holidays, the correlation with the production is 0.85 and is the highest. The headline population index traces the year-over-year change of industrial production pretty well. The performance for specific sectors are mixed as expected. It tracks the statistics well in transportation equipment and poorly in electronic parts and devices on the bottom right-hand side. This could be attributed to what, as we discussed earlier, the fact that the importance of labor input for production could vary a lot across sectors. Since the low data is hourly, we can also construct indices on weekly, daily, or even hourly basis. This figure shows weekly index for transportation equipment. We know that the major typhoon caused serious damage to some factories in transportation equipment sector in October 2019. The sharp decline in official statistics here is vividly captured by our index. So let me conclude. So the takeaways of our paper is very simple. Mobility data certainly has information about economic activity, and it can be useful if we manage to extract related population fluctuations using other data or statistical method. Okay, thank you for your attention.
Thank you, Koji, and thank you for keeping so well to time. So we now have a few minutes for questions.
Yep.
So there's only 20 people here, so feel free to unmute if you want to ask a question. So while we're waiting to see if other people have questions, I've got a couple of things to start off with. So are you currently using these methods in practice at the Bank of Japan for your nowcasting?
Yeah.
And how did it go during the pandemic? Like, obviously the mobility changed a lot. Was it able to accurately track economic activity during the various lockdowns you've had in Japan?
Actually, so yes and no. So first of all, we didn't track this index in a timely manner because there are some like delay in the budget approval and implementation of project and so on. So we did just we just calculate this index with lags of several months, but we also checked performance during the turmoil of COVID-19, and for basically for the food service industry, we track well the official statistics, and also for the production index. But for some sectors like shopping malls, the performance was not well because people changing the spending pattern during this time. So sometimes before the lockdown, people try to buy a lot of things as stocks. So the spending per person increased drastically. So we just count the number of people and just match the pattern before the pandemic. So that our even though we use some machine learning techniques and match the pattern of people with pattern of spending, we couldn't capture well during the spending pattern during the pandemic for shopping mall, because they spend so it depends. So, but I think in general it works pretty well.
Any other questions?
I might just jump in there.
Taz.
Yeah. So I noticed that in some cases, I think you had to aggregate this data because it comes at such a high frequency. So you were aggregating for the week or for the month. But I'm just curious whether you potentially lose any information there. I'm thinking in factories, for example, you might have the same amount of people coming to work, but they're coming in split shifts, or they're changing their working arrangements so that they can socially distance. And you might lose that in the aggregate. And I just wonder whether you've got any ideas about how you would deal with that challenge.
Yeah, that's right. That's right. And we think we can dig more in this aspect. But for the already we use our information somehow. So as I showed, when we choose the when we match the population to the production function, we choose the hour. I mean the window of hours. So for some industry, it's right that the nighttime, the nighttime shift is important to pin down the production level, because in the kind of manufacturing industry, so they produce 24 hours, and maybe they adjust in the nighttime labor intensity. So you're right, but but we believe we can do more. Yeah, thank you for your comment.
Thank you.
Okay, thank you, Koji. We're out of time, so well done. We'll move to our second speaker for this session. Our second speaker is Chalian Pong Kongchiron, who's a assistant professor at Thammasat University. Thanks, Chalermpong.
Okay, good morning from Thailand. Thank you, Professor Hyman, for introduction, and thank you, the organizer, for having me to this session. Okay, today I like to present my paper, now testing Thailand economics activity using the Google mobility data. I start with the motivation. I have been working with some firm about forecasting Thai economy, and we found out that it's hard for us to doing the forecasting in the pandemic era, that the economic activity have changed a lot, and also the government have the policy that they have to implement in order to cope with the economic recession. And it's in Thailand, it's just like most of the developing country, we don't have the data that come up very quick. For example, for the GDP, we take a month and 3 weeks for the data from last quarter to announce. And also for the monthly indicator, it take really long time to announce. So it's hard for us to keep track of the economy and how we're gonna react to the change. Unfortunately, unlike the folk at the government agency, they might have some information and they can require the other agency to collect some data for them. In my perspective, from the academics setting, we need to get data from somewhere else. Like in this case, we found out that we can use the Google mobility data to help us in get the nowcasting and also for the forecast in the other the next quarter also. So that motivated me to work on this project to compare the forecasting performance of the model that using the Google Mobility Index. I use Armax and the MIDAS, the mixed data sampling with the Google Mobility Index, and compare it with just the time series, ALIMA time series, and looking at the usefulness of this mobility index. Okay, so a lot of us might heard about this index. I would like just recap what is this index is. So in the COVID-19 era, Google helped the health community, and also it benefit us to get this index that show the movement of the people from different places. Okay, in this case, Google released the Google Mobility Index that compare the movement each day with the baseline, which is the median value for 5 weeks between January and February. And it tells us the movement in different places like the grocery, the park, transit, retail, and resident, and the workplace. So we can see how people move compared to the baseline. If we're looking at the Google Mobility data for Thailand, so you can see that in this case, around April, that the first wave of and the lockdown in Thailand. So there's a lot of drop in the transit and also the workplace. Okay, and after that, we contained the COVID quite well at that time. So we released, we can travel back to work for some people after that around January, August, and people get comfortable, and there's some case in November, so it had some drop around December. So that the second wave in Thailand. Okay, so I use this data, and there's some work that use this kind of data also that related to this work. For example, some work use this mobility data to forecast about the COVID case, okay, and some work use this Google mobility data to looking at economic activity like Sampi and Joyce in using this data for the Latin America and forecast it with the industrial data like MPI forecasting. Okay, and in Thailand, there's some work that they use this data from Google, like Google Trend, the searching index to forecast the economic activity, like the labor market and also the financial market. And the forecasting performance is work quite well in Thailand too. Okay, so what I did in this work, I compare 3 models. Okay, the first one is ALIMA model. So in this case, I use only the dependent variable here. So it use only past information of the target variable. So we have the longer estimation period compared to the Google index one that we're going to use in the other 2 models. So this might be one dimension that we can look at if you have longer period, longer data compared to the one with the Google mobility that the data that start at January. So that one dimension that we can compare. Okay. The second model that we use here is the ALIMA model with the explanatory variable, the ALIMAX. So in this case, I aggregate the daily data from the Google mobility to be the monthly data to have the same frequency. Okay, and obviously we only have the data from 2020. Okay, in this training period. Okay, so it's shorter estimation period, but I try to figure out the usefulness of using this forecasting. I quote this one from Professor Hyman book that it might be a good idea to looking at this performance here. Okay, and I also looking at the mixed data sampling, the MIDAS, to employ the high frequency feature from the Google mobility. Did it help us to forecast better compared to the ALIMAX model? Okay, and the data, the targeting variable that we're looking at here is there's 2 sectors here. The first one is the service one, is a service production index, SPI, and another one is the manufacturing production index. So for the ALIMAX and MIDAS, it start from it is end at the January 2021. Okay, so the testing period, because we have a shorter Google mobility index, so we have a few a month to compare here. I use the test period just December and January. So keep in mind that we have very small number of training period. Okay, and we compare one period ahead forecast here, and the model selection for ALIMA and ALIMAX used through the November 2020, and then I forecast December and January a month, okay, to get the forecasting. And these 2 sectors is quite big for Thailand, especially the service sector is about 60% of Thai economy, and manufacturing is about 30% of the economy. Okay, So that's why we focus on this sector. The service sector is quite big, and it's moved pretty fast compared to the manufacturer sector. Okay. And the Google Mobility is original is daily data. So some of the model we aggregate the data. Another model is we use the MyDAS. We use the daily data here. Okay. So that the data that we use here. Before we go to the model, I just plot how this service production index and Google Mobility are related to each other. If you're looking at this data, the blue line is the change of service production index. The sub sector is the retail one. Okay. And I plot it with the Google Mobility, the retail one. Okay, and you can see that these two graphs move in the same direction. So it might be a good indicator for us to make a forecasting on the service production index SPI. Okay, so I calculate the mean average prediction errors, okay, as a percent here, okay, and compare the Alimma, Alimax, and MyDAS. And since the Google Mobility Index, we have different places here. So I try to use different index here and see what it like to have different Google Mobility Index. Okay, some might get as the different performance here. Okay, so in this case, let's looking at the retail first. Okay, so we can see that in this case, for the retail, the Alimma give us the MAP is around 1.6%. And if we're looking at the Alimax and MyDAS, we have the case that the MAPE is lower than the one without the Google Mobility. Okay, so for example, for the Alimax, if we use the Google Mobility Index with the park here, okay, the MAPE is smaller, it's 0.2%. Okay. And for the MyDAS, in this case, the retail, the mobility in the retail give us better performance of the forecasting. Okay. Okay, and also for the other sector like the SPI for the transportation here, it's both MyDAS and Alimax give us very good performance compared to the Alimma. Alimma give us 10% error, absolute error here, compared to using Alimax and MyDAS is just 1 or 3% of absolute prediction errors here. Okay. The sector that have been hit hard for Thailand is the hotel. So the drop is quite large, and when we use the Alimma, it give us very long forecast here, because if you use just the data in the past, it's the trend is like the forecasting that we have is quite very long, so really inaccurate here. So if you use the Alimax and MyDAS, that we put the mobility index in the model, it's help us to predict better. Like for the MyDAS, it's just 12% error compared to almost 100% error from the Alimma model. Okay, and also for the information and real estate, the MyDAS and MyDAS work better for the Alimma. And if you're looking at this 5 sectors here. Most of them, the Midas perform better than Alimma in most cases. Okay. However, there's some sector that the Alimma is still work better than the Alimax, like the finance and public administration. Maybe because these two sector might not be changed a lot in the COVID era. Okay, and also the manufacturer, the Alimma model is still work better than the Alimax and the Midas. Okay, so for the conclusion, I think the Google Mobility helped improving forecasting in most of the service sector that we're looking at here. The performance between the Alimax and Midas depends on the sector that we consider, but most of the time the Midas work better than Alimax. Okay, and Alimax perform better when in the finance public administration. That might be quite stable sector, and Google Mobility didn't work for the manufacturing index forecasting performance. Okay, so that's all for me. Thank you.
Thank you, Chalianpong. We've got a couple of minutes for questions. Feel free to unmute and ask them or put your hand up and I'll call on you. So just while we're waiting on that, in your testing period, so you'd fitted these models to monthly data, but I think if I got it right, you only had 2 months of testing. So that's only 2 observations. Is that correct? And if so, how reliable are your conclusions?
Yes, that the drawback of this study, because for the Google Mobility, we only have, now we have 12 months. So we have to use 9 months for the estimation period, and we have only 2 months for the testing period. So that's the drawback of this study.
So another question I have is that one of the advantages of the mobility data is that before you get to the end of a month, you can have quite a lot of information about what's going on. So you can be making nowcasts of your production indices before you see the production index data. That's usually the main benefit of having this sort of daily and unusual data source. Have you tried looking at whether at using the mobility data in that sense, so that you're actually getting advanced, more advanced nowcasts than you would otherwise get?
I haven't tried yet, but thank you for the suggestion.
Anyone else got a question here?
I'll ask the general question if you don't mind. Chalianpong, do you have any sense for certain industries, how they might use these forecasts in Thailand? Like maybe the restaurant industry would find these more useful than waiting for the results in arrears?
Yes, I think for the restaurant, for the hotel is included in this restaurant industry also, and I think the retail might be the big retail is another big service sector in Thailand, so it might be helpful to using this data. Okay. And if for the business part, if they have the weekly or daily data, they can match this with Google Mobility. So I think that might be helpful for them. But I don't have access to that type of data.
Thank you.
Okay, thank you, Chalianpong.
Thank you.
We now move on to the third talk in this session, which is me. Let me just share my screen. So hopefully you can all see that okay. So my name's Rob Heinemann. I'm a professor at Monash University in Australia, and I'm going to be talking about probabilistic ensemble forecasting of Australian COVID-19 cases. This is a little different from what I normally do, in that in this time I'm reporting basically a long contracted research project that I'm doing with various Australian governments. So there's no really new methodology here. at least from my perspective. But I think it's interesting to see how some of these interactions with governments happen and what we can learn about the sort of statistical modelling that's happening for COVID-19. So I report to the Australian Health Protection Principal Committee. That's a committee that's been set up for many years in Australia and makes decisions for national health emergencies. It consists of all the state and territory chief health officers, and it's chaired by the Australian Chief Medical Officer. And they report to the National Cabinet, which consists of the Prime Minister and the premiers of each of the states and territories. So we are providing forecasts to the sort of the highest level of government. We've been doing it every week since March 2020. We're still doing it, and we're going to keep doing it for at least the rest of this year. So what happened was in March 2020, when the pandemic was beginning to show its face in Australia, the AHPPC decided they needed an expert body of forecasters to help them with providing information so that they could then take appropriate policy responses. So they approached a group of epidemiologists at the University of Melbourne and the Doherty Institute. And that group of those epidemiologists then put together a team which included me. So I've listed there on the screen the main people that are part of the COVID-19 forecasting group. There's been some other people involved in different parts of the process, but they're the ones that have done most of the forecasting work. And it's quite diverse. There's people who are well-known epidemiologists in Australia, like James McCaw and Jodie McVernon. There are mathematicians like Joshua Moss. There's some PhD students who sort of transitioned to do this work. There's postdocs, there's statisticians, there's machine learners, and there's me there as sort of the main forecasting person on the group. And so it's quite a diverse collection of people. And we meet every week taking new data as it comes along, and we provide forecasts of daily case numbers for all of the states of Australia to the governments. So we use a range of data sets, and one of the interesting parts of this project is putting together data from all sorts of different places, not just once, but every single week for now nearly 18 months. We take case level data of all the positive COVID-19 tests in Australia. So that's individual people when the onset of symptoms occurred and when the COVID-19 was detected from the test. So we have quite detailed personal information that's obviously got high privacy sensitivity. We also use the mobility data of the sort that the last two speakers talked about from Google. We use similar data from Apple and Facebook. We have weekly surveys that are conducted across the country in every state on how many people are, how many non-household contacts people have, and also how well people are behaving. And so those surveys are conducted every week and we get information from them. And then we grab data from other countries and regions from the Johns Hopkins COVID-19 repository. And so we have daily case numbers from hundreds of different locations around the world. Some of that data is unreliable, we know, because not all cases are getting reported, and there's underreporting, there's occasionally misreporting, there's revision of data. So there's all sorts of data issues in using this in a live context which is directly feeding into policy decisions in Australia. Just to show you what the data looks like, some of the data looks like, this is daily case data for Victoria from the start of July last year. This was at the start of the worst period of the pandemic in Australia, when in Victoria we ended up with hundreds of cases a day. It's the only time that we've been in the hundreds since the start of the pandemic for any state. And this is what the data looks like for all of the states since the start of the pandemic. So that purple line, that's Victoria, the state that I live in, which is where we have the most problems. You see these little outbreaks, which are largely controlled in Australia through quite severe lockdowns when they happen. At the moment, there's a problem happening in New South Wales, and you can see right at the end of the series, the last few days of data, it's beginning to take off, and there's an effort at the moment to try to control that. It's important to realise that case numbers are very uncertain for at least a couple of weeks, and they're incomplete because the date of onset is not known until symptoms show and a test is obtained. So current data, the data that we have for yesterday and the day before and the day before that is not going to be all of the cases for those days, because we're not going to see all of the cases for those days for another couple of weeks because people haven't yet got their tests. And we have to adjust for that when we're producing our forecast. So we're using the data we have, we try to adjust for the incompleteness of recent data, and then we produce our forecasts. The mobility data, which you've already seen a little bit of, looks like this. We're getting data from COVID-19 cases at workplaces. Sorry, not COVID-19 cases. This is mobility data. So this is the amount of time people spend in workplaces, in retail and recreation, and at transit stations. And you can see, if you look carefully, it's fairly cramped because I've got these 8 states and territories and 3 different types of series. And this is just through to February last year. You see there's actually some quite strong seasonality. There's big dips happening. Those dips in the workplaces are largely around holiday periods. This dip is to do with lockdowns and the Christmas period. The vertical bars are where particular physical distance measures have been implemented. Could you please mute your mic during the talk so it doesn't disrupt it for other people? We also get data from Facebook. So this is the proportion of Facebook users who Facebook detected as not leaving the house in each local government area over a few months. And we were looking to see how well the restrictions were being implemented. This is data on non-household contacts per day, which is a combination of data from surveys and Google mobility data. And so the purple line is our estimate of the number of contacts, non-household contacts people are having. And the grey ones are the data from the weekly surveys, which we have to adjust for bias, so they don't exactly match up. And the green ones are the public holidays, and you can see the sort of dips happening when implementations of new policies around restrictions are imposed on different states. And then we have micro-distancing data, which is an estimate of how well people are sticking to the restriction that don't go more than 1.5 metres close to non-household contacts. And so we can measure how well people are obeying the rules in different states, and which are the most compliant states, and so on. So Victoria, where we had the biggest outbreaks, was actually the most compliant state of the whole country, which is sort of ironic, because that's where it took off. And then we have the Johns Hopkins data set, which is data from different regions around the world, not just countries, but right down to regional level. And we collect all of that. Well, Johns Hopkins collects all of that data, we grab it and we build models on it. Okay, so there's a lot of different data coming in here. What happens with our models? So we have 3 different modeling teams who are building independent models of COVID-19. We have a group of epidemiologists who are building sort of a traditional epidemiological model called an SEIR model, which stands for susceptible, exposed, infectious, and recovered. So that divides the population into 4 groups, and it tries to model how the people move from one group to another. So how they move from susceptible to infected, from infected to recovered, and so on. The one we use is a bit more sophisticated than most of them. There's 2 exposed groups and 2 infected groups. And we have a big Bayesian model that brings in mobility and survey data and case onset data and detection times. Daily counts are assumed to be negative binomial, but the parameters of the negative binomial is controlled by a lot of the mobility information. The time people stay in each class is assumed to be a gamma distribution, And then we use a bootstrapped particle filter to forecast the future numbers of cases for the next few weeks, daily case numbers for the next few weeks. So that model is built by a team at the University of Melbourne and at the Doherty Institute. Then we have a second team who's based at the University of Adelaide, and they're using a sort of a agent-based model. They call it a stochastic generative model. And there they divide the population into three groups, three types of infectious groups, that is, the ones that are imported and infectious, the ones that are infectious but asymptomatic, so they're not observed. We never see them because they don't go and get tested. And then we have the symptomatic and infected people. It also uses mobility and survey data and the case onset and detection time data. It assumes that the class counts are negative binomial, the incubation times are gamma, but it's a very different model from the SEIR model because it's trying to model individual behavior much more than just the group behavior. Estimation for this model is also Bayesian. It uses a Hamilton Monte Carlo, and then forecasts are obtained by simulating future sample paths. And then the third model, which is the one that I'm most closely involved with, is actually the simplest. It's just an autoregressive model, but it's a global model. So it's the same model built on multiple series. So we use data from all of the countries and regions, and we clean the data a little bit. We remove series with obvious anomalies, and then we build a single model with constant coefficients across all of the series, but a very long lag. So it has 24 days of information in it. On a transformed version of the case data. So that's sort of like the GERD Gigerenzer said, always, Leni's last night's keynote, always have a simple benchmark. This is our simple benchmark. It's just a one model for all countries. And there's no epidemiological dynamics in that model at all. Then we combine these into an ensemble. So we have a potentially weighted ensemble of the three models. And so each of the forecast distributions are combined in a mixture distribution, also called linear pooling. And this enables us to get the best of all of the different models together. We've actually used equal weights in our ensembling. We've experimented with choosing weights differently depending on the type, the state of that it's in, is it a big state or a small state? And depending on whether it's an upward trajectory or a downward trajectory, we've done a lot of experimentation on weights and haven't found anything that was better than one just equal weighted ensembling. This is what we present to the government. We present a graph like this. These are the case numbers by date of onset. And as you see, it drops down at the end. This is in late June last year, about a year ago. So that's the actual numbers they provide us with. The black dots are our estimated cases before we've seen them all. So we have to do some sort of nowcasting to estimate what the numbers are likely to become. And these are the intervals we provide the governments with. So we provide them with a 50%, 60%, 70%, 80% and 90% prediction interval. And you can see for Victoria, we were predicting at the end of June that this was going to take off probably, which it did. So people ask me, how well have our forecasts done? Every time it's taken off, it's been things that we have predicted are likely to happen. Oh dear, what's going on there? Okay, let me go to this graph. So this is where we're trying to see, well, how well did we do? So this is the case data in retrospect after it's been adjusted for the cases that were not detected initially. And these are our forecast intervals, and you can see that we're pretty good. We're on the low side. We're on the high side. Our prediction intervals are on the high side, but it's within the range. Then a bit later in the pandemic, that's October. A bit later on, this was relatively recently when there was very low numbers, but we're getting it pretty right every time. Occasionally not. So this was in May. We were not predicting it would take off the way it did in Victoria in May. That came under control. this is some of our more recent forecasting. After that recent outbreak dipped down again, this is because of our most recent lockdown in Victoria. Okay, so let me just, was going to talk about CRPS, but I'm out of time. So I'm going to skip over the CRPS explanation and just show you what CRPS looks like for our different states and different horizons. So there's the three component models, the generative model, the global AR model, and the SEIR model, and the ensemble. And you can see that the SEIR model actually doesn't do very well for three of the states, but it does extremely well for Victoria. The generative model from Adelaide does very well for three of the states, but it does very badly for Victoria. My global AR model, the simplest one, does pretty well for three of the states, but it does badly for New South Wales. So every model is doing well some of the time, but not all of the time. The ensemble is a way of sort of combining them. So the red line here, 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 and here is sort of a compromise between the different models. And this is based on weekly forecasts at different horizons for the four biggest states in Australia. What have we learned? We've learned that diverse models are better than one model. It's really important to understand the data. Don't just take data as you're given it, because there's all sorts of stuff going on, and the data custodians, the people that collect it, know best about what's going on, and you need to talk to them. I've seen a lot of COVID-19 forecasting which just takes off-the-shelf data from Johns Hopkins, does a forecast and doesn't really engage with all of the issues about reporting problems. You need to have a very well organized workflow when you're doing this week after week, and communicating probabilistic forecasts is difficult, but if we've been able to do it by having a very consistent visual design that the governments are now very used to and understand what we mean when we talk about probabilistic forecasts. Okay, that's it from me. There's how you contact me. My slides are on my website if you want to have a look at them. Any questions?
This is a great talk, Rob. This is Jerry. So I have one question. Yeah, so in the models, you have an ensemble model, but then beneath that, there are three models. Do you guys consider, for instance, the virus variants and people's behavior and the vaccine, that kind of a bigger effect?
Yep. All of those go into our models. So all three of them take those things into account in different ways. But we have, I presented only three models, but there's actually several variants of some of them because of the different variants of the of COVID. And as you know, we currently are having a Delta model and an Alpha model, and we're presenting both of those sometimes to the government as required. We have to re-estimate our model regularly based on changing the changing infectious rate of the disease as different variants come into Australia. So all of that we're trying to build into our models, yeah. And as the rules change on mobility, we have to adapt the model to new changes there as well.
Yeah, so in the US, some people are reluctant to get the vaccine, maybe provide a kind of a scenario-based forecast. Okay, so we get this high level of acceptance for vaccine, and that level, and then the corresponding projections will be good for the government. Yeah, so sometimes the government will come back to us and say, can you give us a scenario forecast that if this happened, what do you think will occur? For my global AR model, I can't do that because there's no dynamics in it. But for the other two models, we can run scenario forecasts, and we sometimes do as the governments request them.
Rob, can I ask you a question? Now, did you experiment with COVID deaths? These are infections, right?
Yeah, so our contract with the government is simply to provide them information on case rates. There are other teams of people working in Australia on other things, including hospitalizations and mortality rates and things like that. But that's not what we've been asked to do, so I haven't looked directly at deaths.
Yeah, because death also is a very tricky variable to track because there's so much revision goes on. Finally, when you finally get the death records, there's a huge discrepancy between what the CDC reports or Johns Hopkins and what finally comes out after 6 weeks on the vital statistics, you know.
Yeah. I'm well aware of that. And there's the excess mortality rates are actually often more useful than the official death rates for that reason.
So that's another problem. Another thing is that have you tried like some of the American companies, for example, IHME out of University of Washington? I think they do all countries, maybe including Australia. Have you seen some of the American farms who give forecasts for Australia? Maybe you can use them. Have you checked them? I'm not sure.
I haven't seen any Australian forecasts done outside of Australia. We are in touch with other groups that are doing things like this, and we swap notes. Nicholas Reich, for example, is heading up the US group for the CDC, and we are in touch with his group sometimes.
You mean the Amherst, UMass group? UMass.
Yeah. Last question from Fan Cheng.
Thanks, Rob. Quick question. Is there any precaution if your model has predicted like a huge increase in the numbers? And what if several models show different conclusion because especially across different states?
So I'm not quite sure what you mean by the first question. So when our model shows there's a huge numbers, we just report that to the government and they have to make a decision about what to do. They sometimes
I was wondering if the government is doing anything if you are predicting an increase.
Oh, yeah. So these are feeding directly into decisions on lockdowns. I mean, that's a somewhat political decision about what they should implement, but they definitely take account of our forecasts. And in many cases that I'm aware of, they have taken action because the forecasts have shown, the forecast that we provide has shown them what's going on. And we provide state-based forecasts, so every state's different.
Yeah. Sometimes the Victoria has shown a great increase in the model, and sometimes it's New South Wales, but different model give you different conclusion. What if that happens?
So we provide an ensemble forecast for each state. So they're just one forecast for each state, which is based on the whole ensemble. And each of the governments will decide what to do with that. So if Victoria's going up and New South Wales going down, those governments will just take different decisions. But it's a state-by-state forecast and state-by-state decisions.
Okay, thank you.
Thanks, Fan. We're out of time, so let's leave it there. Thanks to you, everyone.